speculate most of you are here because you received one of these in the mail. If you didn't, it's because we don't have your address and you are not a member. But hey, guess what? We've got these. And you can sign up, and our treasurer, Mrs. Shelley Bad, is right in front of me, is right here. And if you are not a member, please, you are welcome. She'll be happy to take your check or your cash tonight. And we have more of these out on the credenza and also back there on the table. Our newsletter then will highlight the rest of our lectures for this year. And I will let you know that our next lecture will be July 4th at the Athenaeum, and that starts at 10 a.m. And Sagamore the Wabash recipient Andrew Wilson will be our keynote speaker on July 4th. And our declaration reader this year is Mrs. Karen Rozier. You're not going to want to miss that. Additionally, I got to get my dates right, on June 14th and 15th is our Friends book sale that coordinates with our Antiques Festival. And our scheduling coordinator, Mrs. Donna Creek. Donna, you want to raise your hand? Hey, Donna's here with the sign-up sheet.
Opening for the book sale.
She's got openings. So if anybody is free and would like to volunteer for a shift, please see our scheduling coordinator afterwards. And hey, if you don't, she's got your number and she's calling. Just let me know. Matt, how's it going? Close?
Close.
Okay, all right. Well, so I'm going to talk a little bit about our keynote speaker while he finishes setting up. So, our keynote speaker tonight is Dr. Matt Rebeck. And Matt's day job, he is the school neuropsychologist. I'm going to read this to make sure I get it right. Neuropsychologist and psychologist at Mount Vernon Schools Corporation. And additionally, he is an adjunct professor at the University of Southern Indiana. Matt earned his undergraduate and master's degrees from Indiana State University, and his doctorate in education he received from Oakland City University. And besides that, he owns several postdoctoral certificates and other kinds of educational stuff that he can put behind his name, and that's fantastic. But when the day ends, when his day job ends, his passion for all things space take over. And so, fortunately for all of us, his wife Terry gifted him with one of these magnificent pieces of equipment during the pandemic. And that's why we're all here tonight. So at any rate, as Matt says, as Dr. Rebeck says, tonight we're going to take a trip through the cosmos from the Rebeck's backyard. So at any rate, Matt, do you want to, I'm just going to go like this. Matt, maybe you want to talk to us a bit while you're setting that up? Or I can have my husband come up and tell jokes.
All right. The official introduction, Matt Rebeck. It's a pleasure to meet all of you guys. Thank you again for your patience. All right. So, like Jeannie said, I kind of stumbled onto this wonderful hobby during the pandemic. It was that first winter, and my wonderful wife, who knows me better than I know myself, knew I needed an outlet. And she got sick of me, I think, being in the house. So she's like, oh, well, I can get him out of the house and have him busy, so telescope. So I started off about a year in visual astronomy, and this is the very first telescope right here. Hopefully everyone can see it with the column there. And this is called the Arbogast, which is named after a ship from, it's called the Expanse novels, a set of 9 books about space. Really enjoyed it. So loved it so much, we started naming our telescopes after that. So the Arbogast was my very first telescope, hung on to that for a couple years. or a year. And then I had what's called aperture fever and had to upgrade to the 10-inch telescope, okay? And this is called the Behemoth, okay? And then after that, I jumped into astrophotography and it was over after that. So I'll go through the details of all this stuff and all that. So anyway, so that's the background story. So if anybody has any questions, I know they prefer them to be asked at the end, but I get it. Sometimes there's just that burning question you have to ask. So if that's the case, raise your hands, no problem. The only thing that I don't really want you guys to ask about would be the cost of specific equipment. Now, if you are interested in getting started and you want to know about budgeting and that kind of stuff, absolutely. Find me after this and we can talk. But other than that, if you have a burning question, raise your hand. At least let me finish my train of thought and I'll get you. Sound good? All right. So, because I hang out with educators so much, anytime there's a presentation or anything that we're doing, right, I have to tell you what I intend to teach you, right, reiterate what I teach you through scaffolding, and then ask you what you've learned at the end. But don't worry, the quiz is very easy. It's open book. So, all right. So anyway, here's the basic organization. So we're going to go through just the basics of astronomy first. The organization of space, constellation and stars, the different classification of nebulae, which is plural for nebula, classification of galaxies and star clusters, and the equipment. Then we're going to jump into basics, very basic of astrophotography, equipment, the process. There's always a process, right? How to shoot deep space and how to shoot solar photography as well. And then we're going to end with picture gallery and some cool facts. So I hope you guys like it. Okay, so without further ado, space is a pretty big place, isn't it? So how the heck are we going to organize it? Well, it's actually organized very similar to the way we organize directions here. Anywhere on Earth, there's a longitude and a latitude direction. Same with space. Anywhere in space, there is what's called right ascension, which is space's version of longitude, and declination, which is space's version of latitude. So on a telescope, okay, what that looks like, other side, this right here is the right ascension. Okay? And then this right here is the declination. So you put the coordinates in to the telescope system and it, boom, points at it. Just like that. Now the way objects move in space, which we will talk about, after the object is found, the declination doesn't really move, but it's the right ascension that moves. Like this. Okay? All right. So, for example, and this doesn't even mean anything at all to me, but if you wanted to know, the exact coordinates of Andromeda Galaxy is right there. Right ascension, 0 hours, 42 minutes, 44 seconds. Declination plus 41, 16 minutes and 9 seconds. There we go. Okay. Everything in space has coordinates. So here's just a visual representation here. So that little ball there in the middle is Earth. So think about the longitude and latitude, or right ascension and declination, going out into space. Okay? Just like we have an equator on Earth, there's also a celestial equator. And just like we have a North Pole and South Pole, space also has a North celestial pole and South celestial pole. Okay? So that's how, that's how the directions are made and everything moves. Now remember, it moves in relation to Earth. Earth is the one that's moving. Okay? Everything in space does move, but Earth moves much quicker. Right? We are revolving around the sun. The sun is revolving around a supermassive black hole in the middle of our universe, and our universe is moving around too. Okay? Everything moves in space. It's just a question of how fast and around what. Okay? All right, so we have different ways to name things, right? Instead of that fuzzy patch in the sky, look at that. People long ago came up with standardized ways to name things So someone can say, hey, I want to look up NGC 6943, and you know exactly what they're talking about, right? Now, there's a lot of different ways to classify objects because there's a lot of stuff in space. But this is just some very, the more popular categories, okay? And I'm going to reference some of these when I'm talking about objects and things that I have taken pictures of as well. So we have the Messier catalog, so that's been noted as an M and then a number, okay? For example, Andromeda is M31, okay? Now, if you're looking for something you can see through like even binoculars or just a very basic telescope, anything in the Messier catalog is good to go, okay? They're very bright, and he actually started that catalog because he was trying to find comets. But he actually found a lot of stuff that was not comets, so he was ruling those out, and then he ended up making his own catalog. So, there you go. We have the New General Catalog, NGC. We have the Index catalogs, and then we have Lind's catalog of dark and bright nebulae, and then we have Sharpless. Okay? Again, many, many more. And then there's also the nicknames. Okay, and that's kind of the fun stuff, where people look at it and they're like, well, I think that looks like a jellyfish, or that looks like whatever. Okay? And it's kind of fun to see that, hey, I see this, but you see this instead. So taking a step away from astronomy and into my psychology hat, wearing my psychology hat here, it's kind of like a Rorschach test when you're looking at space stuff, right? But then I follow up with, I say, how does that make you feel? I know, we spent a whole semester on just saying, how does that make you feel? I'm not supposed to tell you that, though. So. All right. So oftentimes, these catalog objects have more than one name. For example, the Veil Nebula, which is the nickname, can be called NGC 6960, which is a part of the Veil Nebula. It's huge, which we'll get into that. Or it can be called IC 1340, and Sharpless 291. Okay. A lot of times with these objects in space, they have a primary name. Like, again, Andromeda is M31, but this also has an NGC and et cetera, okay? But lots of overlap, okay? So, everybody good so far? Okay, am I making up for my tardiness?
Yes.
Or do I just have to prove myself? That's fine. All right. Drink break here. Cheers. Okay. So, constellation and stars. So think of constellations as like country or state boundaries, okay? And the stars are cities, right? There's some countries that are bigger than others, so there's some constellations that are bigger than others. And just like there's some cities that are bigger than others, there's stars that are bigger than others, okay? Now that is also taking into account what's called absolute magnitude and relative magnitude, okay? So magnitude is the way that we measure star bright, or anything in space really, brightness, okay? So absolute magnitude is the actual brightness. Relative magnitude is the brightness from our vantage point. So there's a star that's huge, really bright, but it's really, really far away, so it's just a teeny tiny pinprick, right? On the other hand, there could be a real tiny star, but it's really, really close, so it looks very bright to us, okay? So scientists have a way of measuring those kinds of things, okay? And then there's asterisms, which are the shapes within the constellations, which is what we are very familiar with, like the Big Dipper, right? That's actually that's actually an asterism within an asterism, because the Ursa Major is part of the bigger constellation of the Big Dipper. Okay, the Big Dipper is just kind of the tail end of the bear. Okay, but that makes it very easy to remember. Okay, stars, got that. Okay, good. All right. I know you want. Okay, a lot of talking, a lot of verbiage here. So how about a picture? All right. So here is one of the most famous constellations, Orion the Hunter, which is also believed to be the oldest identified constellation, where scientists have seen cave drawings of a constellation that looks very similar to Orion. Okay. So we see a couple things here. First, we see the border. Okay. This is the border, and it's surrounded by these other constellations, right? And then the size of these stars are different. Okay, that is the measurement of their magnitude. The smaller the number, this doesn't make a whole lot of sense. They didn't ask me about it. The smaller the number, the brighter the star. Okay? And see, Canis Major right here, which is the hunting dog of Orion, the hunter, has the brightest star in our sky called Sirius. This is more of a winter kind of constellation. Okay? But we see the belt of Orion, and then we see the sword up here, and then we see the bow right here. Okay? Just a beautiful constellation, and there's just a lot going on. And you can point your telescope almost anywhere in here, and you're going to get something. So it's pretty cool. Now there is it's called the Witch Head Nebula, which I'll get into, which is right by this bright star. So that does make it a little bit more of a challenge to capture, because you don't want to blow the star out and blow out your information you're trying to present. And then when you process it too, you have to be very careful with that. So anyway, so there's the constellation of Orion. And here we have Ursa Major, the Big Bear. Okay, so I was telling you the Big Dipper is kind of the butt end of the bear. Okay, but the constellation itself is huge. It's very big. It takes up a huge portion of the sky, and right now it is up. So once it gets dark, depends on the clouds. Probably not tonight, but you can see it right now. It's up right now. It is a circumpolar constellation, which we'll get into. But right now, springtime-ish is the best time to view it. There's also a ton of galaxies in it, which we'll get into that as well. So, but we can see the border here of Ursa Major is actually very big, isn't it? And then we have the asterism, and then the asterism within the asterism, and then the constellations on this borders. Okay. Everybody good so far? All right. I don't hear any snoring yet, so I think I'm doing good. All right. We've actually designated somebody to wake people up very harshly with the shock in case they're asleep, so I'm just saying. Okay, so another important reason for constellations is because that gives us a point of reference. Okay, so when we're looking at something or when there is an object, we can say in the constellation of Cygnus. Okay, and for you Rush fans, in the constellation of Cygnus, there lives a mysterious black hole, Cygnus X1. Now within the constellations, there's classified as circumpolar, zodiacal, and seasonal. Okay, so we'll get into what those mean. Circumpolar is the constellations clustered around either the north celestial pole or the south celestial pole, depending on which hemisphere you're in. For us, we're in the northern hemisphere, so it's the NCP. So they never set below the horizon. They're always moving around, okay? Where our zodiacal and seasonal constellations, they go away for a while. We don't see them. Like Orion is gone, pretty much. You might see a little bit of his bow or a sword hand, but that's a winter constellation. So he's pretty much done for the season. And for I'm not exactly too familiar with the southern hemisphere constellations. I do have a couple friends from Australia, though, a couple astro buddies, and it's really weird because everything is upside down. So we're used to seeing the hunter one way. The hunter in the southern hemisphere is upside down. So I asked them, like, why are they upside down? And they're like, it's upside down for us. And they look at your side. All right, so the constellations that are circumpolar for us: Ursa Major, the bear; the Big Bear; Cassiopeia; Cepheus; Draco; and Camoparadalis, which is Latin for giraffe. Which I don't know why I said giraffe, but trying to trip me up. All right, so this is a shot of the circumpolar constellations. Now this is if we were at the Arctic, the most northern point, okay, of the Earth, and we lay down. Hopefully we don't lay down in the snow or ice. This is what you would see. The further north we are, the higher up in the sky Polaris is. Okay, so if we get down to the equator, Polaris is almost dead ahead. Okay, we're at 38 latitude, north latitude here, so Polaris is about like this. Okay, which is perfect because it's just over the trees in my way, so it worked out. So as you see, we have our circumpolar constellations here, so they move around like this. Okay, now Polaris is known as the North Star, and it's very, very close to the North Celestial Pole. But scientists hypothesize that in a few million years, because everything moves in space, Polaris will no longer be the North Star. Okay? But right now, it's very close to the NCP, the North Celestial Pole. So it's very easy for people in the Northern Hemisphere to find the North Celestial Pole. The Southern Hemisphere, they don't have that. Okay, they have to use other tricks and trades. Yeah. All right, everybody good still? All right, cheers.
I have a question.
Question, yes.
If you're in the northern hemisphere in the old days, you would navigate off the North Star. If you're in the southern hemisphere, what do you navigate off?
That's a very good question. I could ask my Southern Hemisphere friends. I do know they have the Southern Cross that's very prominent, and it kind of pointed, and it's used as a reference, from what I've read, it's used as a reference point for finding the South Celestial Pole. But that's a very good question. But I'm not exactly sure. But I can find out for you. Oh, speaking of navigation, okay, I'll get into that. All right, so zodiacal. All right, so we've heard of the zodiac and all that kind of stuff, what it means. All that it means is that the constellation at one point traverses through the ecliptic of the sun, or the sun passes through the constellation. That's all that means, okay? The sun and then obviously the planets follow the ecliptic. So that's why every now and then we get all the planets lined up, because they're all following the sun, okay? So that is just what those zodiacal constellations are. It's Aries, Taurus, Gemini, Leo, Cancer, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. Okay? And there is some overlap between the zodiacal and the seasonal. So here's just an example. Okay? So there's all of our zodiacal constellations. Now, there's a little bit of scientific debates about Ophiuchus, okay? Where some believe Ophiuchus is a zodiacal constellation, some do not. So I'll let you make that decision. I'm not here to persuade you one way or the other in the heated Ophiuchus debate. So we can see from our vantage point, okay, during the day, here's us, right? Sun is shining on the side of the earth that we are on, and Aries follows through that the ecliptic, the path of the sun. Okay. And then seasonal, I talked about that a little bit, right? Orion is a winter constellation. Scorpius is a summer constellation, which Scorpius and the summer constellations are just coming up, which also means the Milky Way is coming up as well. And we are fortunate enough that we are in a very low light pollution place here, where you can look up and you can see the Milky Way. You kind of have to know how to look, and you have to give your eyes time to adjust. It takes about 30 minutes without light for your eyes to become dark acclimated, okay? Now, you can use a red light. I've got a little lantern, but it's a red light. That the red light does not ruin your night vision, okay? So, the seasonal, okay, so a little story. The reason why the Greeks, at least, thought that Orion and Scorpius were at different times of the year. They never crossed paths, right? Orion is a winter constellation, Scorpius is a summer. Is that Orion the hunter was very boastful, a very boastful hunter. I can kill anything, right? And the gods wanted to teach him a lesson, so they sent Scorpius to kill him. He couldn't kill Scorpius. So the gods put both Orion and Scorpius up in the night sky, and Scorpius chases Orion forever across the night sky as a reminder to not be caught. Okay? So, yeah, and there's all kinds of cool stories about that, which I'll get into a little bit too. And it's a really good way to learn about the night sky, where you have that meaning behind it. You're just not looking up and seeing a W or an M, depending on time of the year, in the sky. Say, oh, that's Cassiopeia. Be like, oh, that's Queen Cassiopeia. She was boastful about her own beauty and got her daughter into trouble, but luckily Perseus was there, etc., which we'll get into. A little teaser for you guys. Okay, so the way that the seasonal constellations work as well is we can only see the constellations when our side of the Earth is facing away from the sun. That's nighttime. Because stars are up all the time, right? It's just a matter of can we see them or not. So different constellations are prevalent at different times of the year. Now, it's not an absolute thing. Okay, like I said, or you might be able to get a little glimpse of Orion. So it's not just the day of spring, Orion's gone magically. Okay, these times of the year are the best times when the constellations are up high enough, where it's really neat to see them. When they're low on the horizon, they actually have to look through more of the Earth's atmosphere. So you get a little bit more atmospheric disturbance, so they actually turn a different color, right? We see that the most with the sun, when it's red, right? When it's close to the either horizon. I'm doing this because this is west, that's east. But when it's up in the sky, it's not red, right? That's because of our atmosphere and particles in the atmosphere, etc. So, for example, Gemini, best time is around December 21st. February, Leo, but Leo is still up, so it's kind of a cool constellation to see. Kind of looks like a question mark, or backwards question mark, or a sickle. Let's see, I'm going the wrong way here. All right, Cancer is up now. Very cool star cluster. Gemini, June. Okay, so anyway, seasonal constellations. All right. Oh, it's my reminder. I have a guest talk at the Workman Man's Institute. I think I'll probably turn that off. Okay, I'm there. All right. Man, yeah, if I was just getting packed up, we'd be all in trouble, wouldn't we? All right. So the northern star is called Polaris, which is very close to the NCP. It's used for navigation purposes prior to Google Maps, or even maps at all. The more northern you are, the higher up in the sky it's going to appear. So here is, now this is not my picture, and in my kind of photography here, if you see that, you're in trouble. It means your mount's not working, okay? Something's not working here, okay? This is bad for my stuff, but this is kind of a cool representation here. So we see how close the NCP is, and then we see the North Star. Okay. Now remember, stars don't move this way. They look like they move this way because the Earth is rotating. Okay? All right. Making a lot of trips here, so maybe I'll be a little bit more efficient with my time. All right, and here's kind of an easy way to find the North Star, where you find the tail end of the bear, the plow, or the Big Dipper, and you have these two stars here that are pointer stars. And then you just follow these up to Polaris. And there it is. Okay. So, yeah, play around with that. See, it's kind of neat to see if you can find a constellation or stars before, using the app or something like that, or a star catalog. Okay, so we're moving along maybe a little quick. Everybody good? Not overwhelmed yet? Good? Okay, all right. So, classification of nebulae. So there's the fancy definition here. I know everybody can look at that. Pretty much what it is, it's just some dust and clouds up in space. Okay. A lot of times, these nebulae are stellar nurseries. Okay. However, by forming stars, because all the gas and dust condense down, they're their own worst enemy. Because once the stars are formed, once they have enough mass to start creating nuclear fusion, they start throwing out radiation, stellar winds, those kinds of things, which then dissipate the nebulosity all around it, the nursery. Now, cool thing for us, though, is that it creates some pretty cool shapes. So we can take pictures, or nifty little pictures of that, okay? So here we have different kinds of nebulae. We have emission, we have reflection, dark, and then supernova remnants, okay? All right, so now an emission nebulae involves energy. So the radiation, the energy from these young, hot stars, then they remove an electron. Okay, so it's called ionizing, if you want to be technical. They remove an electron. So what happens there is then that creates energy. So then these nebulae have their own energy source. They're actually creating their own, so they're glowing. Okay, which makes it very easy to find. So this type of nebulae is not dependent on another star to reflect off of it or anything like that. It's creating its own energy. Okay. But then, like I said, the young, and when I say young, in space terms, a star that's about 1 million years old, that's young. That's very young. So, and then birth of stars lead to stellar death. Okay. But then the matter is never really destroyed, right? It just changes form, and something like a supernova or some kind of other catastrophic stellar event can coalesce the stellar matter again, and we start the process all over again. Okay? Or when the star blows up, it throws that matter out into space, and then it's there again to condense to create stars. Okay, the emission nebulae, that's the majority of the nebulosity up there in space. All right, finally got to something that I did instead of stuff that everybody else did. This is called the question mark nebula, for obvious reasons, right? Now, it looks like it, but this little dot here is nowhere near this nebulosity here, nowhere near. But from our vantage point, it looks like it, right? And this is huge. I took this with a lens about this big. Okay, it's in one of these bags here somewhere. Pull it out later. Some people say it looks like a skull as well. Because all this nebulosity is mostly hydrogen, without any specialized filters, which this is one of the first pictures I took too. Everything's going to look kind of red or salmon red. Okay. Now you can use other specialized filters to bring out more detail in different kinds of gases, which I'll get into. But this is an example of emission. Okay. So this right here, this nebulosity, it has its own energy. Okay. It's very excitable. Okay. It's very glad that there's stars forming because now it gets to glow. Oh, it's in Cepheus too. That star field is massive too. That's really a pain to process out. Okay, then we have reflection nebula, where these nebulae, they do not create their own energy. They're just dust and gas just chilling in space, but there's something around them that's illuminating them. Okay, it's almost like if you hold a light behind a leaf or something like that. The leaf itself has no energy, no light source of its own, but you hold that light and then it glows. Okay. Oftentimes these can be paired with emission nebulae, which that's really cool to see that as well. This is also mine. This is called the Witch Head Nebula, for obvious reasons. Now this right here I was telling you about earlier, this is Rigel. This is again one of my first pictures I took, so I had no idea how to deal with this, so it's really blown out. But the Witch Head itself has no energy source, none. But this star is so big and so bright, it's illuminating all this gas. Okay? And this is actually a supernova remnant too. So it's a star that exploded, and that's the gas that's left. And then the red in the background is all hydrogen, and you can't really see it too well, but in the witch's hat, there's a bunch of little teeny tiny galaxies. Yes?
As you're showing some of these pictures, just to give a conception how much time it took.
Yeah, that would be in the later.
Okay.
But I feel like I'm already kind of overwhelming. Now, just to notice off the top of my head, that's about 8 hours worth of data. So as far as the projects that I normally work on, that's actually quite a shorter amount of time. But it's so prominent and so bright, you don't need a ton of time. But yeah, when I go through the gallery and facts, I'll talk about more of the details of all that fun stuff. But that's a very good question. All right, in the dark nebulae, these are very interesting, where they really don't have anything illuminating them either. Okay, so they are just mostly gas, cold gas and dust, but they form really cool shapes, and they are between us and the stars in the background. So from our vantage point, when they block the stars, we can see those shapes. Okay, these can be more difficult to capture because they're dense, so it needs a little bit more integration time. And thankfully, and processing skills, thankfully YouTube is there, so I follow step by step. So I don't know what we did before YouTube, but all right. So this is it doesn't have a nickname actually, but this is an example of a dark nebula in Cepheus. It's part of a very large molecular cloud. Okay, that's huge. It's I mean, it would take a lot of work to even get a fraction of that dust up there. So that's just an example. You can see there's nothing glowing. And even that star down there really is not illuminating anything. It's just gas and dust right there. Terry and I, now because there's no name, we looked at that and we thought it looks like a rubber chicken. So we dubbed this the Rubber Chicken Nebula. Was that yours? Yeah. All right. And I'll go into details too about all the fun stuff there. Supernova remnants. Now these are really cool. Stars had exploded in space. There was a cosmic explosion, and we see what's left. Because of the makeup of stars and because of the reaction of those elements after such a cataclysmic event, we're able to capture some really cool wispy clouds of gas, a lot of hydrogen and oxygen as well. So most of these supernovae originated from stars at least 20 times the size of our own sun. And that's about the bare minimum to go supernova. It's 20 times because it has to be big enough when a star dies, it collapses into itself. So the life of a star is always a balance between the significant mass that it has. In our case, the sun makes up 99 or 98% of the mass of our solar system. Okay, so our sun is an average sun in its midlife. Okay, so it might be picking up a hobby sometime soon. Who knows? So a star has to be big enough that when it expenses its fuel, its hydrogen, and when it starts making heavier elements like iron, that's the depth of the star, where it collapses into itself into a violent collapse and then it explodes out. Where it can also go straight into a black hole if it's big enough, or supernova black hole. Okay, which we'll get into a little bit, and I have some examples of that as well. This one is mine. This is probably the most famous supernova remnant called the Veil Nebula. And this thing is huge. This is only a portion, and this is even a 2-panel mosaic. So what that means is the thing is so big, I could fit everything in my field of view with the bigger scope. The black one is called the Rocinante too, by the way. I couldn't fit the whole thing with the Rocinante, so what I had to do was take about right here, half and half, and then use software and stitch them together. Okay, but this is only a portion, or this isn't even half. The Veil Nebula is, I have this down in the slide. Let's see how well my memory is. About 3 full moons big. So you have 3 full moons in the sky, 3, maybe 4. That's how big it is. And my wife is very good about pointing out objects to me, so I showed this to her. You know the first thing she said? Looks like a fish. Now you can't unsee it, can you? No, can't unsee it. There's the mouth, eye, there's the fin, there's the tail. Yep, there we go. All right, I just ruined it for you. Sorry. Okay, so the reds are, the red in the nebula is hydrogen, alpha, while the blues are teal, oxygen. Okay. All right, now we're on the galaxies. You guys are experts in nebulae now, right? So galaxies, now there's a ton of sub-classifications with galaxies, so I'm not going to go into that. But broadly speaking, galaxies are classified by their shape. We have elliptical, we have spiral, and we have irregular, okay? So the elliptical is, just as I said, it's just kind of an oval, round shape. It's really not visually, aesthetically pleasing to look at. It's kind of neat to understand the history of the elliptical galaxies. A lot of times these are galaxies that are dying. There's not a whole lot of star formation going on. Stars are dying. They're not creating new stars, those kinds of things. Okay, and they're usually pretty small too. So it's a little bit harder with equipment without having really big equipment to resolve them. And even if you do, it's not as cool looking, but cool to study. Now, this is an example of 3 galaxies here. These are in Ursa Major. So the elliptical galaxy is the one way up here, okay? Now that one, I did, in processing, I did my best to really bring out some of the reds in it, the hydrogen in that galaxy. But that's an example of an elliptical galaxy, and I will go into detail about all the other stuff going on. There's a lot going on in that picture, isn't there? So I will touch on that when I go through the gallery there. So. And that's an example of the elliptical galaxy. And then we have the spiral galaxy, which is the most common. And there's many subclassifications about the black hole. Is there a black hole or not? The shape of the spiral, and all that fun stuff. Just pretty much the spiral. I already know what that is, right? These galaxies have a supermassive black hole in the center where everything is moving around the supermassive black hole. Okay, just like we are in a spiral galaxy. Andromeda, Milky Way, Triangulum, which is all three in the local group, we're all spiral galaxies. We all have a supermassive black hole that we are rotating around. And this is the Triangulum galaxy. Here's just an example, and we can definitely see, and it's kind of neat the orientation of the galaxy to us, the Earth, that we can kind of see the arms here. Okay, and we'll see how that is a spiral. And I won't go into detail about all the other fun stuff going on there, because again, I just want to make sure we get on the basics, right? We have to build that foundation before we go to the higher order stuff, right? Okay. Learn to crawl before we move the telescope. Okay. Then we have the irregular galaxies here. They lack any kind of definition or shape. Sometimes they are due to gravitational interactions with other galaxies. Sometimes they're just formed that way. The two most famous irregular galaxies are the large and small Magellanic Clouds, which are actually satellite galaxies of us. We have two galaxies that are rotating in orbit around the Milky Way. But unfortunately, they can only be seen in the southern hemisphere. But they are absolutely beautiful. My buddy in Australia likes to rub it in. But you can see it with the naked eye. You can just look up, and there's another galaxy orbiting around us. So, but I do have an example. We have here, now, I'm not sure if you've noticed this or not, but a lot of times in these pictures, there's more than one galaxy, right? Galaxies like to hang out in groups, okay? They're not solitary beings, okay? They are drawn together gravitationally, so a lot of times they'll be called a group of galaxies, okay? So this is a group. Now, this is the irregular galaxy here, and we can see the little patch of galaxy up here, and it's got the hook shape, and it's just a mess, Plus it's hard. It's trying, though. So that would be an example. And then the galaxy on top, that's called a whale galaxy, because it looks like a whale. That would be a spiral galaxy adjunct. So instead of like what we saw with Triangulum, kind of like this, where you see the cool spirals, it's adjunct. Okay. All right, so we have different kinds of star clusters as well. We have globular and open star clusters. These are really cool, too. So, broadly speaking, a globular cluster is very old. They are as old as our universe, as old like billions of years old. Okay, or billion, like 1.3 billion, right? So these are very old stars. Okay, they're stuck in their ways. They don't like change. Okay, so we have then the younger renegade rebel stars, right? The open clusters. These stars move around a lot. These are young. Young stars burning through all of their fuel. There's a lot of times these stars only last a few million years, which is again very short for stars, and then they just burn through their fuel. Okay, and it's believed our very own sun came from an open star cluster called Pisces 24, which is an open star cluster in Scorpius, 8,000 light years away. So what that means is our star was formed. It did something it shouldn't have. They kicked them out of the group. They flung our star 8,000 light years away to where it's at right now. A lot of times when things are flung, like slingshot, it's because of gravitational interactions. Okay, so gravitationally, our sun was interacting with stars, and then it got flung 8,000 light years away to where it is right now. And here is for a bonus. Here we have where our sun is in relation to our own galaxy. But I chose this because we see where these globular clusters are at. Okay, they're actually above the plane, the halo of our own galaxy. Okay, so what that means is a lot of times when we're looking more in the north and south, we see a lot tight sometimes that they'll bump into each other and create new stars. That's how close these some of these clusters are. This is my picture here, and this is the great globular cluster in Hercules called M13. And Hercules is actually coming up now in the sky, and you can see this with your naked eye. Now, the moon will have to be not there, not present at all. Okay, you have to be adjusted real well, night vision, and you have to have good eyesight too. So, but a pair of binoculars, it's a really beautiful. Telescope, it will look really nice. So, anyway, so that is an example of a globular cluster. Now, this is not mine, but this is Pisces 24. This is where we came from, right here. Okay, this open star cluster here in Scorpius, and then our sun was cutting up, so they kicked them out. And here we are today. Okay. This is probably the most famous open cluster. This is my picture here. This is the Pleiades, or Seven Sisters, or if you want to be technical, M45. You can see this with the naked eye, and it looks like a tiny little dipper. So we have the Big Dipper, the Small Dipper, and then, I don't know, Dipper Junior, or Dipper to the third, okay, whatever. Now, you're not going to be able to see the nebulosity there, okay? When this was first discovered, they thought that the nebulosity was part of the cluster, but it's actually in between us and the stars. So we're just lucky enough that we get to see the cool nebulosity as well. Okay, so you can see it now. It's pretty much, if it's not gone for the year, it's pretty much gone. This is more of a Taurus, is where it's located. Taurus is more of a winter constellation. Okay, but naked eye for sure. Binoculars looks great. In fact, the behemoth there, that's too big. I can't get it all in the behemoth there. So beautiful though. All right, everybody still good? Okay. All right. All right, so equipment. 3 types of telescopes. We have refractors, reflectors, and catadioptric. Okay, so the refractor, okay, this right here uses lenses. Let's see if I took this one off. Very scientific tape. Okay, so it uses lenses here to gather light. Okay. And then it focuses it onto a point, just like that. Now these scopes are built for visual, and you can use them for solar, which I'll get into. But they're pretty much, it has a lens. Now the really expensive ones have multiple lenses. Okay, and the price really jacks up pretty high. Any kind of camera lens, that is a refractor that you have. Okay. So there you see Saturn there. The light comes in and converges to the eyepiece. All right, and then a reflector uses mirrors. Okay, so we have a couple reflectors here. The Rocinante here is a reflector. If you can see that, I'll take the shield. Bless you. So now, please excuse the mirror. I need to clean it. But a mirror this size, though, the dust will not have too much of an effect on it. Everybody see it? You guys see it over there? Okay. And then this over here is also, that's an 8-inch aperture, the opening. This is a 10-inch. So same thing. This is just built for visual. This one's really dusty. So. All right. Walk through the maze of telescopes. All right. And then catadioptric. Unfortunately, I do not have an example yet. Now, what a catadioptric telescope does is it's kind of like you put these two together. If they got together and had a baby, it might look like a catadioptric telescope. Okay. So what it does, it uses a combination of mirrors and lenses. And what it does is it folds the light. Okay. Which what that means is that you can get a really zoomed in either view or picture. Okay. In a very small package. Okay. So this is 900 millimeters focal length, which we'll get into, but something this size right here, even smaller, This is 800 millimeter focal length, which again we'll get into. But you can have something this size that's a catadioptric, which is 2,000. So 2,000 is much bigger than 800. Okay. And here's an example. They're more complicated. They can be a little bit more expensive, but actually, cost-wise, they're really not too bad. So this is how it works. The light comes in. It's a little bit more complicated. So the light comes in. They have a primary mirror back here, like we do with the reflectors, and then it bounces off into a lens here, and then from the lens it goes to the eyepiece, the eyeball, camera, whatever you have at the other end. Okay. So a little bit more complicated, but you get really a really big telescope in a small package. Okay. And here's just a quick view of all three together. There's a refractor, reflector, and catadioptric telescopes. All right, so the aperture is the opening. Okay, the opening right here. So this is an 80 millimeter aperture. This is 90. This is 200 millimeter or 8 inch, and then that is a 10 inch and 250 millimeter. Okay. So the aperture has to do with gathering light. That's the main purpose, the main objective of the telescope is to gather light. Our eye is 2 to 8 millimeters. Okay, teeny tiny holes that can gather just a very small amount of light. Okay, that's why there's a limit to what we can look up and see in space. Not because of eyesight, because of light gathering power. So we had these. It's like as if we had two eyes that were 8 inches, right? What we could see. Okay, that might look a little funny. Okay, so focal length. There's the technical definition. Really, what it is the distance from the lens or mirror, okay, to the eyepiece. Okay. So the longer the focal length, the more zoomed in you're going to be, okay? The shorter the focal length, the wider field of view you're going to be, okay? So just as an example, this smaller scope here is 400 millimeter focal length, so wider. 910, the Arbogast, so tighter. This is 800, and that one over there is 1200, okay? Then F ratio is the way that we measure light gathering, okay? So even though this is 910 focal length, right, we think that's pretty good. This system is an F10 system, which means it's kind of slower at gathering the light because you look at the aperture and then divided by the focal length. Oh, I forgot to warn you, there's going to be math. Did I say that?
No.
Oh, sorry. All right, next presentation, I'll warn you guys. Okay. So, and this is a 200 millimeter focal length, or aperture, 800 focal length, so it's an F4 system, which is very quick. Okay. So there you go. There's the specs there. So F4 is very, now the faster your optical system is, though, the more prone it is to error. Okay. That it's very sensitive to any little shift. Say the camera moves a little bit, it's going to ruin your pictures. Okay. You don't culminate or line up the mirrors just right, your pictures aren't going to look good. Okay. So shooting fast is really cool. But it also comes with its disadvantages. Okay, there's also systems as fast as F2, which is twice as fast as the Rossi there. So anyway, so the Arbogast has 90 millimeter focal length. Now there's the solar filter, which I will get out in a little bit. But the solar filter that I have that I attached to this to take pictures of the sun has a built-in magnifier to it. So this turns 910 focal length into almost 4,000. So that turns it into an F43 system, which is crawling. That's slower than a turtle. But the sun is so bright, we don't need that. In fact, the sun is so bright, we need filters because it's too bright. Okay? So an F43 system is crawling, but that's okay for the sun. Okay. Okay, so the eyepieces, you add an eyepiece, you divide it, okay, by the focal length. So what that means is the larger the eyepiece, the less zoomed in it is, which I have. All right, so this eyepiece here, okay, that is 27 millimeter, okay? So this is a wide field. Now this one right here is a 11 millimeter, so this is very small, okay? This would be if I wanted to take a look at something like the Pleiades or something like that, okay? This one is beautiful with the behemoth looking at Saturn and Jupiter. So the different sizes.
Which one for Jupiter?
This one. Planets are tiny but very bright, so you can really zoom in. The further you zoom in, the greater magnification that you use on an instrument, the dimmer the object can be. But things in the solar system are so bright anyway, that doesn't matter. Okay, so that's why when you're taking pictures of things like the sun, the moon, the planets, you can use the telescope and really zoom in, and it can be a really slower system, but they're so bright, it doesn't even matter. Okay. All right. All right, so mounts. This is the foundation of the your astrophotography or astro setup here. You can have the best telescope in the world. You can have the James Webb shrunk down version, but if you don't have a mount that can handle it or you can hook it up to, it's going to do nothing for you. You won't be able to take any pretty pictures. You're not going to be able to see any pretty things. So all three of these are equatorial mounts, but different sizes. Okay, this is actually the first one I started off with. And I have all this stuff used here. But the idea, equatorial mounts, this one, sometimes they're called German equatorial, this one, this one, this one. You get them pointed towards the north celestial pole, and then, just like I showed you before, after it finds its target, let's say its target is right there, okay? It'll lock down the declination, and it just follows it. Just like that. Now, you'll come to a point, about right here, called the meridian flip. Because it keeps going, oops, actually this has a built-in feature for people like me. But when it gets to a certain point, the system will say, all right, time for the meridian flip. So it knows the object is about right there. So then what it will do is then it'll go like this. Oh, calling the cables. So anyway, let's just pretend the object is over there. But then it'll flip like that and then track it through the night sky. Now, if there was no such thing as daytime, it'd come to another meridian flip and then flip it, or it'd just go continuously, okay? But this is, all three of these work the same, it's just different sizes, different payloads, okay? Where this one is a max of 12 pounds, okay? Now, if you're using any of these for astrophotography, they recommend half. So if it has a 12-pound limit, then you want to stay around 6. You don't want to go any more than that, because then you're going to have tracking errors and throw out all your stuff, because it's long exposures, which I'll get into. So 12 pounds, this is my next upgrade. 40 pounds here, so that means I can have about 20 pounds worth of equipment. And then this one over here is 80 pounds, so I can have about 40 pounds. So this telescope right here barely touches it. This telescope is like, is there anything on me? Or the mount, is there anything on me? So, which of course means I have to upgrade, but anyway, it never stops. They call it the black hole hobby, right? It just never stops. All right, so here's an example of a fork mount, which I do not have. Kind of works the same principle where it's just a fork that hooks onto the side of your telescope. And then here's an alt-az mount, which means it moves up and to the right, up, right, left. So it's not very good for like deep space astrophotography, but visually and planets and moons, that you can use that as well. So, and that's an example of a catadioptric telescope right there too. Okay, everybody still good? All right, Rick, give me a break.
A million years ago, I had one tennis like that, but it was all mechanical. Now
Yes.
they're all computer controlled.
They can be. I'm glad you brought that up. I forgot to talk about this. The biggest telescope here. All right. Thank you, Rick, for bringing that out. This is, there we go. This is a reflector, just like the reflector over there. But this is on a Dobsonian mount. Okay. Now this is called a Dobsonian mount because an amateur astronomer on the West Coast, San Francisco Bay Area, named John Dobson, actually came up with this. And it's a really neat way just to survey the sky and move it around. Now this is for visual, maybe some moon photography. The moon doesn't move too much, but mostly for visual. So you just find whatever you're looking for and look through the hole there. But John Dobson was a pretty cool dude. He put on workshops where he would take families, even some like inner city kids and stuff like that, take them out to the stars and have them make their own telescopes. These kinds of reflectors are somewhat easy to make, where he had a workshop and they made telescopes and then they looked at the moon and they got to keep their telescopes that they made. So really cool sky. Yes?
Do these do any absorption of movement of the Earth or anything? Like if a truck drives by or something?
Oh,
and,
I got you.
I mean, is it absorbing any of that, or is it?
That's a really good question. Now, as far as a truck or anything like that, it's not going to vibrate a whole lot. These are heavy enough. Each one of these counterweights are 22 pounds. So, and then you have the head and then the telescope. So it's a lot of weight pushing down. Now, if you are in a place though that does have some vibration, they actually make little pads that you can put underneath each foot, and it absorbs that vibration. Or some people would like set up on their decks and stuff, and they'll use those pads and that kind of stuff. So, thankfully, we haven't had any earthquakes or any big trucks in the yard that would do that. I set up far enough away from the road, but so when you're walking and stuff like that, you still have to be kind of careful too. You don't want to walk too close. If you walk too close, you could bump into it. That wouldn't be good. But for the most part, they do a pretty good job. The ground is very good at absorbing the shocks. So, very good question. Yes.
Well, what I'm thinking is, when I had mine, I had to very carefully get on the North Star.
Oh, yeah.
And then just have a little electric motor that if I didn't have it lined up perfect,
Yeah.
it wasn't going to follow.
Mhm.
Versus the modern ones, you tell it where you are, what you want to look at,
Boom.
and then
Yeah.
it just follows.
Yes, absolutely.
So working with that is what made me give it up. Versus,
Yeah, they have the ones now too, like this, where you can. It's called a go-to. These mounts are also called go-to, where it goes to the celestial object that you want it to. So you just type it in, the little coordinates, and it goes to it. It has Dobsonian mounts out that would go to as well. What this one will do is it can say what you want to look at, and it'll tell you how far off you are, and tell you like move left 2 clicks or something like that. So that's very good. Very good point. Everybody else good here? All right. Still away. I know. Oh, lots of stuff here. Okay, so for astrophotography now, the mount is more important. In deep sky astrophotography, I'm taking long exposure. So most of the time I try to do a 5-minute exposure. So that means the camera sensor is open collecting photons for 5 minutes. Okay? Just like what was said, any little bump and it shakes, and that 5 minutes called a sub frame or picture, that sub is ruined. Okay, so the mount has to be spot on. The mount has to be doing its job. You have to get everything balanced and lined up. So you can see here that this is balanced. This is good. Now, if it wasn't balanced, it'd be moving one way or the other. So if I had this counterweight too far down here, woo, look at that. See, not balanced. Okay, if you try to shoot with it like this, you're going to have a bad time. Okay. So the cameras are also designed for long exposure photography as well. I'll take care of that later. So we have our optical corrector. So the fast telescopes, like this, all right, you have what's called coma at the end, where the stars look like comets. Okay, that's where they got the name. So you have a coma corrector, which you put on to the end of your optical system, which corrects for that. So here's an example of my deep sky camera. Okay, right here, this piece of glass here is the coma corrector. Okay, it's a real pain because you have to space the coma corrector to the camera sensor just right. If you don't, then it's going to look bad. And the faster system is more prone to that kind of stuff. So this deep sky camera has a cooling system in it. Okay, that's because the sensor is open. It's collecting photons for 5 minutes at a time, which then induces noise. Okay, so the system cools it down. You can set it to 20 degrees below ambient, where you'll minimize that noise. Okay, with just a deep space. Okay, so here is an example of the camera I use for the sun. Okay, built very different. Okay, deep space, the sun, or planetary. Okay, so the moon, planets, stuff like that. This is for long, slow, tedious type work. Okay, 5-minute long exposures. taken over 8 hours. This right here, it can take, this one in particular can take 20 pictures per second. The other one I have down in there that I can dig out can take 150 pictures per second. Okay, so when you're taking pictures of the solar system, like the sun, moon, stuff like that, you want to go very fast. Here, you don't want to go fast. Okay. All right. Okay, autofocuser. So this little red thing here is the autofocuser. So I can hook that up. Show it to everybody here. What I have to do is take apart the focuser a little bit and then hook this up. And then this is hooked up to the whole system where I can autofocus at the beginning of my routine. I can try to focus the best I can with my eyeball, but it will never be software. So what it does is it looks at the most in focus star and where the focuser is at. So I can't move the focuser because it's hooked up. And then what I can do is throughout the night, I can set it to refocus after 2 hours. After 1 hour, it'll automatically refocus. I can be sleeping in my bed, dreaming of wonderful dreams of psychological work the next day. And then every 1, 2 hours, you can set it, have your half hour. You can also have a temperature gauge on it, so if the temperature changes, it'll automatically refocus. Now the reason for that is because when temperature changes, when it cools down, it loses focus. The focus point changes a little bit. Now we're talking about astrophotography, so millimeters are miles here. Okay, so any little change, the picture's gonna be out of focus. So you can refocus that, and it's all in the system. You just all set that and go. Okay, so filter wheel. I didn't show you that. Okay, so this is the filter wheel. I have different filters in here depending on what I want to shoot. Okay, so there's some filters that are better for galaxies, some filters better for emission nebulae, some filters better for reflection. So it depends on what I'm shooting. If I want to shoot multiple targets in the night, I can say, shoot this for 3 hours at 5 minutes per picture with this filter, and then shoot this for 4 hours using this filter, etc., etc. Okay, I program all that into the system, and it just goes. And it just, so, there we go. All right, software control. All right, so, as far as software, everything is controlled, believe it or not, with this. Okay? I hook all the wires and all that kind of stuff up to it, and it's Wi-Fi, so I can control it with my iPad sitting inside the house. I set it and forget about it. Okay?
That's why you're never out there.
That's why I'm never. Well, you just don't see me. You know, it's dark out.
See the
Camouflage, yeah. All right, so guiding system. Okay, so you may have noticed a small scope on top of the big scope. There's a reason for that. Hopefully everybody can see that here. So the guide scope has its own little camera. Okay, little teeny tiny camera, which is right here. This is the guide scope camera. Okay, so you hook up the guide scope camera back here, and then what it will do is it will track the movement of stars throughout the night, and then it will send a signal to the mount, hey, you're moving too fast this way, slow down over here, those kinds of things. So it will make those corrections throughout the night for you to make sure that you have really good, sharp, not blurry pictures. Now, really high-end mounts, you don't even need that. Like the stuff they use for science, not for fun, they don't even need that. Their mounts are so good, there's no error at all, or very little with their tracking. But with my mounts, I do need that guiding system. So, and then the camera, which I talked about. Okay, so here's just an example of what the stars in my system would look like with no corrector, and then those two, the MPCC and Skywatcher. Don't worry about the name, those are just different kinds of chroma correctors. Okay, so you see the difference though, right? Now we were lucky enough, we live in a fortunate enough time that there's now software that can even correct for some of these star issues through artificial intelligence, AI software that can recognize that it's a star and there's an error with that star and make that correction. Yeah, technology. Yeah, the guy used to be an engineer. And he has some other softwares out there. This is all he does now. He just makes software for astro. But engineers make the best astrophotographers. This is just an example of what the filter wheel would look like inside. I don't want to take mine apart for you guys. No offense, please. But that's what it looked like. So you just screw in these little filters and then, yep. And I do have a filter somewhere around here in my. Okay, so the process. So planning. So we need to find the size of the target and the equipment. So if I'm shooting, with this is my main astro rig. Is the target really teeny tiny? How is it going to look in my system? All right, or is it really, really big, and do I need to create a mosaic of the target? Those kinds of things. Time of year. All right, if I want to shoot an Orion right now, I got to go to the other hemisphere, don't I? Okay, Orion's not up, so if I want to shoot an Orion, I'm out of luck, right? And then also moon phase. Some of these targets are very susceptible to the moon. When there's like a full moon out there, that's like having a little sun, and it washes away those details. Okay, so depending on where I shoot in the sky, what I'm shooting, those kinds of things, I can use a filter that blocks out a lot of the moon, but still may not be worth it. So then after I decide what I'm shooting, then I set up the equipment, which if you were here, you saw me doing that. So that's me doing that, but sometimes when it's really cold and all bundled up, or really hot, and then I balance the equipment like I showed you with the counterweight, and then polar align. So you get real close to the NCP, the North Celestial Pole. So you have these adjustment knobs. There's one right here, and there's two down here. So you set the software for polar alignment, and then you get down here, which is probably why you never see me, because I'm down here all the time. You take a picture, and then you adjust. It tells you which adjustments to make. And then you get real close to the North Celestial Pole, and you stand close enough, and you call it. And the same thing for this one. And same thing for that one. And this one actually has well, this one doesn't, but this one and this one have little scopes that you look through and to line that up. It's not as accurate as the computer, never is, but because that's really wide field, it doesn't make a big difference. So then you set the plan. Like I said, I want to shoot with this filter. I want to shoot this target for this amount of time. You set all that in, and you hit go. And then there's the stacking. So some of these projects are 40 plus hours. That means I shoot it night after night after night after night. So I have hundreds of pictures. So there's software out there where it takes all the pictures and it stacks them together into one picture with really good, what's called signal to noise ratio. Okay, so a lot of these objects are very dim, so you have to take numerous exposures, numerous pictures, night after night after night. Now with the sun, that's very different, which I'll get into. So think of taking pictures of anything in the solar system as opposite of deep sky. Okay, so you stack it all together and then you process it. So there's like things like Photoshop, which are not necessarily designed to process deep sky, but you can make it work. And then there's also software out there that's specifically designed for astrophotography. They made it just for that. So here's some screenshots here. So this is a project. Actually, I haven't had a chance to process this yet. This is M106. I believe it's in Ursa Major. Don't quote me on that. But here's what the interface looks like. So here I have the exposure time, 300 seconds or 5 minutes. Here I have the meridian flip is in 4 hours when the telescope's going to flip, right? Here I have the cooling, so the camera is cooled to negative 10 degrees ambient, so I can check on that. The gain, which is like ISO, is 100. There's my field of view, and there's my guide up there. And then right here, M106, all right, it was up there, wasn't it? All right, so that's 2 pictures out of 100 that I'm taking that night. And up there is target 1 out of 1. So I'm just shooting the one target that night. So anytime I can pull out the iPad and look at it and see how everything is going. And then the guiding graph up there in the upper left corner tells me how well the guide system is doing. Yep.
So you can real time work on your iPad and see more or less what the telescope is saying.
Exactly. Yep. So with the guiding, we have the error in the right extension declination. Without getting too technical, as long as your total is less or right at 1.0 or less, we're good. You're going to get good summers. So this is a pretty good night. I was at 0.4, so guiding is good. And this is one sub. So this is what one sub looks like. So you saw some of the pictures, right? So this is just one 5-minute sub. Okay, so we have a cool galaxy here. There's some cool stuff. I really like the 3 stars up there. So this is actually my next list of process. I'm actually looking forward to getting this process. So anyway, so that's the interface. And then here we have a more detail of the guiding. Okay, so if you click on the guiding graph, you get, some people love to really get, I mean, this kind of hobby, you can really dive deep, okay? Or if you just want to take pretty pictures, that's cool too. But here, you have the correction you can set, and then here's your guiding graph. So that's the error, okay? And again, I'm at 0.26, so I was doing something right that night. I wish I could remember that. And then see, it locks onto a star, and the system measures the movement of the star against when it calibrated how the star is supposed to move with the mount. So the mount will actually move around when you're calibrating to get an understanding of how the stars move, or supposed to move as your telescope moves. And when the star is not moving that way, the mount, it sends a signal to the mount saying, hey, you're messing up, wake up. Okay? This guy has a presentation, he wants to show off his pretty pictures. Okay, and then there's the size of the star there, so the size of the peak. So anyway, so that's the interface for the guiding. So there you go. And then here's part of the planning mode. Now this is the Rosette, which I did take, I have that to share. But this is part of the planning where this thing is so big, there's my field of view right here, one of these, okay? And that takes into account the size of the telescope and the size of your camera sensor. So I say, I want to take a picture of this, but it's too big, so I'm going to do a 2-channel mosaic. And then you can also set the amount of overlap and where you want to take it. You save that, and then night after night, you can just click on it. Telescope has the coordinates saved in its database, and it goes to that. You say, I want to shoot panel 1 for 3 hours, panel 2 for 2 hours. With this or for that. So. Okay, so solar is a bit different, and when I say solar, this is also kind of the same with anything in the solar system, okay? Where it's small, and it's, well, the sun's not small, but it's bright, it's very bright. So you actually want to take very, very short exposure. So that camera, right here, so I'll take like 1,000 pictures, okay, which will, my other camera, which is better, this is more of like the full disc, which is slower, but it's because it's a bigger sensor. The other camera, though, I can get 1,000 frames, 1,000 pictures in about 8 seconds. Okay, so the sun is very unique because it's the only object in space that changes by the minute. Okay, so you can look at the sun 1 minute and look at it maybe 5 minutes later, and it can look completely different. Okay, so you don't want to take a whole bunch of real long pictures. Now the moon doesn't change. The moon hasn't changed for millions of years. Okay, so you can just stick your camera on there and just fire away. It's not changing. Okay, but the sun is a very dynamic, very active celestial object. And I wish I had the skills to do what's called a time lapse, where you see the solar flares or the prominences shoot up into space and all that kind of cool stuff. But that's beyond my expertise right now. I've been doing solar for a little over a year now, I think, or something. I'm still pretty new. So, all right, so this is really cool. I don't know if anybody has been following the news lately, but some really cool news about Planet 9 and Planet X. Okay, about 10 years ago, there was a group of scientists that thought, they still think, that they have mathematically proven that there is a Planet 9 out beyond Neptune, far, far out there, because the way that they discovered these kinds of things, which Neptune was also discovered this way, it was discovered mathematically before visually, is that scientists understand how things in space are supposed to behave. And then when they're not behaving that way, they say, what could be going on? So there's a group of scientists that thought and measured the behavior of these that are called trans-Neptunian objects, okay, beyond Neptune, behaving, and they say, well, you know what, we're thinking that there's going to be a planet out there 1.5 times the size of Earth. So super Earth out there, hanging out, way, way out there, okay? They believe if it does exist, now remember, this has not been confirmed, they have found something, though, they need to investigate further, okay? What they had to do is take data from 20 years ago, because if there's a Planet 9 that's moving very, very slow, it's about 800 astronomical units away. So 1 astronomical unit is the distance between us and the sun, which is 94 billion light years or something, or 94 million miles or something like that, okay? Which light travel, it takes light 8.5 minutes to get to us from the sun. So light, you travel that distance in 8.5 minutes. But, so they have 800 AUs, astronomical units, way, way out. So it moves very slow. So they have to look at data that over a large span of time, okay? So anyway, kind of exciting that this came up as I was putting the PowerPoint together. So, but remember, they have not confirmed it. They have just found a candidate that they need to either rule in or rule out. That's the way good science works. Okay. Okay. Photo gallery. All right. Everybody else good? Anybody need a bathroom break or a stretch break or anything? Are we good? All right. All right. Here we go. All right. So first one here we have the Cygnus Loop, which is the official name. There are all those fancy NGC categories there. With this particular project, I had 22 hours on it. And cool fact is a star that exploded 10 to 20,000 years ago and is 20 times more massive than our own sun. 6 full moons. I don't know, did I say 4 last time? 6. And it's expanding at a rate of 932 miles per hour. Okay. So here is, again, the Fish Nebula. Okay. And then here is a closer up version, and that is called the Witch's Broom, nicknamed the Witch's Broom. And a little bit closer up too, you can kind of see some of those filaments, some of the more faint gas kind of dispersing. You see that bright star there in the middle of the frame that looks kind of cool. And then here we have Pickering's or Fleming's triangle right here. I kind of like the way it gives it kind of a 3D, kind of look almost like a comfy chair you can sit down in it. But you know, all this was a star that exploded 10 to 20,000 years ago. So I think we're about in the Bronze Age when it exploded. So it'd be very interesting to see, to interview those people, right? To figure out like what were you thinking with this star that's brighter than Venus that can be seen during the day.
How much exposure time on that one?
Oh, that's a good question. 22 hours? Yeah, 22 hours. And this is a 2-panel mosaic, so about 11 hours each panel, stitching together. Yeah, good question. I should have said that. Okay, so next one. We're going to talk about that one. So it's between Orion and Uranus constellations, and it's a reflection and a supernova remnant, and 8 hours on that. So there's the witch head again. Very prominent though, and very, very big. I took that with the telephoto lens, so it was about this big. Okay, so it's a very, very big nebula. Next here we have the Jellyfish Nebula. It's located in Gemini, and total integration time is 25 hours and 25 minutes. It's a SNR, supernova remnant. It exploded 30 to 35,000 years ago, and it's about 5,000 light years away. So what that means is this is what it looked like 5,000 years ago, because that's how long it takes light to travel and make it to our planet. So we see it's the toe of one of the Gemini twins. I'm not sure if it's Castor or Pollux, but that bright star also makes it a little bit tricky to process. But there's also a lot of cool nebulosity for a wider field of view too. But you can see more of the blues and the reds that are very characteristic of supernova remnant star that exploded.
Special filters on that?
You got it, yes. I use a special filter that is designed specifically for oxygen-3 and hydrogen alpha. And there's different wavelengths of light. Just like there's different wavelengths of sound, there's different wavelengths of light. So these filters are designed very specifically to allow the light from hydrogen alpha and oxygen-3 to come in and wash everything else out. Yeah, very good question. Okay, here we have the Bubble Nebula. It's in Cassiopeia. This is 44 hours and 27 minutes of integration. So the star that created the bubble is 45 times more massive than our own sun, and it's 7 light years across, just the bubble part. Now, as a point of reference, our solar system is about 2 light years, depending on how you measure it. But about, if you're going out to the Oort or Oort cloud, about 2 light years. Okay, so the bubble itself is 7 light years big. And then we also have the star cluster down there. And then there's also the Lobster Nebula, which is real close to it. I got a little bit of the call there, that blue up there, that's the claw of the lobster claw nebula. So again, that bubble there is expanding because the star is 45 times more massive than our own sun, throwing out that radiation, that energy. Okay? All right, it's called the Rosette or the Skull Nebula. Monoceros is the constellation of the unicorn, and that is a wintertime constellation. It's actually right next door to Orion. Total integration time was 34 hours, and this is a 2-panel mosaic, and 5,000 light years away. I used a special filter designed for oxygen and hydrogen alpha. Some people call that the Skull Nebula. Yes.
You collapse the stack stitch first.
What was that? Sorry.
You collapse the stack or stitch first.
Oh, that's a good question. I stitched the panels separately and then stitch them. I stacked the panels separately and then stitch them together. Yeah, very good question. But the way I did it here was I did about half. So about half there, up like that. Okay. And we see the hole or the eyeball, right? And some people say it's the skull, that's the eyeball, that's the nose, that's the other eyeball. But because there's all these stars right here are very young, hot stars that are blowing the gas away. So it's creating the rosette or skull shape from there. Okay. So the blues tend to be more oxygen, while the gold and reds are hydrogen alpha. All right, Ghost of Cassiopeia. Here we have 33 hours, 45 minutes. Now this is a very big area of the sky too, about 4 full moons worth. So this is just a fraction. This is cool because it's reflection and emission nebula. So you can see where it gets its name from, right? Looks like a ghost here. Now the blues here and blues up here, that's the reflection part of it, okay? This star right here, Gamma Cas, or Navi, is the middle part of the W asterism in Cassiopeia. So if you look up there and you see that W, you're looking at the Ghost Nebula, even though you may not be able to see it. You're looking in that direction. Okay? So that star is super massive, super bright. So it's eroding away that nebulosity, which will eventually, nothing will be there. But we have the advantage of seeing these really cool shapes. So. All right, Pac-Man Nebula. I think it looks like a whale, but you know. We have 27 hours worth of integration.
Is that the ancient name for it?
Yes, that's the ancient name. Yep. That's actually where the game came from. Constellation Nebula first, then game was based on that. This also contains what's called Bok globules, which are small, very black, dense nebulosity. Okay, let's see if you can find it. So, see, it looks like a whale to me because that's the mouth, that's the little tail right here, and then there's the spout right there. So Bok globules, all of these little areas here. Very, very dense star forming. And you can see how the young bright stars have eroded away this part here, okay? Creating these cool shapes. There we go. All right, so this is a really busy part. There's all the actual names. Now, there's actually no nickname for this part up in the sky. And I found this just by dumb luck. I was out there, night sky, got everything all set up, and I was like, I don't know what I want to shoot. So I was just looking around, and I was like, all right, well, this place looks kind of cool. So anyway, I got 26 hours on this. The main target I actually found, this is Sharpless 2135 right here, and then I call the word up there is Lens Bright Nebula as well. So, and there's a little star cluster down there too. Kind of cool part of the sky, not really well known. Sometimes it's kind of cool to shoot stuff that's not really well known, just to see what you can get. So, all right. So here is a very rare target, and I found this by dumb luck as well. When I was just searching around the night sky. This is nicknamed the Lizard Pillar. And it's in Lacerda, which is the lizard constellation, which is right by Cygnus. It's very dim, so I needed 44 hours on this. And it was only discovered in 1975. So space terms, that's pretty new. I used 2 special filters. One filter to isolate the hydrogen alpha, and then one filter to allow more light in to give it a natural look. So that's the lizard pillar. So we see the brighter, the hydrogen alpha regions here, and the low hydrogen alpha regions out here. And what I kind of like too is the way it looks like a tremor. Remember that movie, Tremors? Kevin Bacon. Kind of looks like it's going after this galaxy. It's going to try to eat that galaxy. Now you might see some of these right here, and you're like, why didn't you throw those subs out? You're talking about how big your guiding is. These are actually little tiny galaxies. Okay. And the AI system is in tune enough that it can recognize the difference between a star and a little teeny tiny galaxy like that. Because one way to process is there's another AI software or plugin that it will remove the stars. Because stars are so bright and this stuff is so dim, and if you're trying to bring it out, you'll blow out the stars. All you'll see is bright stars. So a way to do that is you take the stars out, process it, and put the stars back in. All right, Tulip Nebula. All right, so this is really cool. 31 hours here. There is actually a black hole in frame. So I'm going to see if you guys know cheating. I saw the look on your face, Jeannie. And this is also believed to be the first black hole discovered called Cygnus X1. Okay, so again, if you're a Rush fan, you definitely know what we're talking about here. That area emitted a very strong what's called X-ray source because of the radiation, just because there's so much power, there's so much mass being taken in by the black hole that there's a lot of energy output, okay, where they can detect X-ray sources in our own galaxy and other galaxies, but we can detect other black holes by measuring the X-ray amount. All right, so there's the Tulip Nebula. It's in Cygnus, which is, it's a pretty cool, funky kind of nebula all on its own. This star field is massive too, so I definitely had to take the stars out and I can shrink the stars too. Because if I just did it with the stars the same size, all you see is stars and a little bit of touch of nebulosity. Okay, so there's the tulip right here in Cygnus. Any ideas where the black hole is? Can you see it? Right there. Actually, that's the star that it's eating. We can't see the black hole. Okay, it's a trick question, sorry. I couldn't help myself. Now, just like when I was talking about Planet 9, how we don't necessarily have to observe the object itself, but observe the environment around the object when something's behaving like it should, and you ask yourself why. You can see this very faint bow shot, right? That is from the black hole. This black hole right here, Cygnus X1, is so greedy, it's eating up this star. It's cannibalizing that star. It's taking in the star matter, and if we eat ourselves, if we eat too much too fast, what happens? Burp. So this black hole is burping up matter at such an incredible, almost unfathomable speed that it is creating this bow shot that's huge, like millions of light years. So there you go. There's Cygnus X1 with the tulip.
Was your intention to get the nebula and that happened to be there, or was your intention to get the black hole?
Both. I knew they were both. Yeah, that was my target. Yeah, that was. This was not. Even though some of them are by chance accidents, this was not. So yeah, I actually planned this one for once. So, but that is a really good question. All right. So here we have the Lion Nebula. It's in Cepheus. This is a 2-panel mosaic, and it's 50 hours, so about 25 hours per panel, where I use, again, special filters that isolate hydrogen alpha and oxygen free. Can you guys see the line? Now, the line itself, the head is much bigger compared to its body. So this right here is the big head. There's the eye, the jaw, there's its tail, and there's its hind leg here. So the head is very, very big. Can you see the line yet? Or do you see something else? What do you see? I just see a bunch of colors and stars. But we have all that. Some places are more dense with the gas and less dense. That's just because of star formation. The stars, young stars, are pushing all that gas away. All right, California Nebula. This is 28 hours worth. This is why it's called the California Nebula. Okay, it's in Perseus. This one star, this one lonely star right here, is responsible for lighting all this up. This is emission, so the gas is electrified. Okay, And I believe looking through a telescope, you can kind of see it. I mean, you have to know kind of how to look through the eyepiece and know what to look for. All right, Heart and Soul Nebula. So we have Heart and Soul, and then we also have a star cluster there in Cassiopeia. The heart itself is very big, covers 4 times the moon, 22 hours. So this is a really cool example of, now the stars have been created for a while because some of this stuff in the heart here is almost non-existent. It's very thin nebulosity here. I saw the Soul Nebula just because, heart and soul. But looking at it, someone told this to me, and I can't unsee it, but it looks like a buffalo. Now, this buffalo is facing down, where that's the head, that's the mouth. There's the little legs, you see it kind of running. And there's open star cluster. There's a star cluster up there in Perseus. So this right here is actually on the borderline with Cassiopeia and Perseus. Because over here, we're in Cassiopeia. Over here, we're in Perseus. Over here, we're in Indiana. Over here, we're in Illinois. Okay? So, I mean, the line is like right there. Okay? But yeah, another example of an emission and what that star formation can do to the gas. All right, so this is a pretty busy place too. I have a wide field view and a closer view of a couple. So we have the flaming star, tadpoles, spider, and fly nebulae. Okay. So here we have, this is the tadpoles nebula. Now once you see the close-up picture, I'll show you this again, you see the tadpoles. This tadpole right here, this is spider and fly, and then this is the flaming star nebula. Okay, and then here is M38. And M38 will always have a special place in my heart because it was the very first, I'll break my leg going through, tripping through memory lane here, literally tripping, right? That through the arbor gas there, that is the very first celestial object that I found through the telescope. And I can remember it was cold, of course, we had that after Christmas. Running inside, and I forgot to take my shoes off, but I was cracking snow and mud in. But very free and stuff. I'm very proud of myself there. So, anyway, there's a lot of stuff going on here, right? And from our vantage point, it looks like all this stuff is clumped together, right? It's not. The tadpoles is much, much further away, but it's also much, much bigger. The flaming star is very close as far as space terms are concerned, but it's much smaller. But from our vantage point, it looks the same, doesn't it? Okay. So close up. Now this is taken with my, here it is. With this. This is my very first setup here. I hooked up a DSLR, which I did bring to, right here, and put it on that little mount and prayed for the best. So that, and it also gives you an idea of how big that area is as well. So this is 135 millimeter focal length, and the big scope is 800. Okay. So, closer up views here. This is the flaming star up close. That's with the Rocinante there. What's really cool about this is we have emission, but we also have reflection. The blues right there. So I did my best to bring out those blues because I felt like they really stood out with the other nebulosity there. And this star right here is responsible for all of this. Right there. This is one little star right here. And I processed this in a little different way. Because it's a flaming star, I want to give it this appearance of almost being like on fire. So I went for more of a red, kind of deep red kind of color. So I hope I pulled that off. So, anyway. And you'll notice, right, the little cross on the bright stars, that's called diffraction spikes. And that is due to the optical system here that it's called the spider vane, which holds the secondary mirror in place somewhere, right here. Okay? So anytime you see those diffraction spikes, it's probably set up like this. Okay? Now you can add them in using software as well. So if you shoot with something without diffraction spikes and you just like the look, you can actually put those in. So. And now here is the tadpoles nebula. Okay? So I went for kind of a look because they're tadpoles. I went for a look to try to make this almost look like a cosmic pond here. So a little bit different process again that I normally do. These tadpoles themselves are about 10 or 11 light years long. 10 or 11. Remember, our solar system that we have just passed through not too long ago, about 2 light years. 10 or 11. Just like that. numbers. I know, mind-blowing, right? Keep you coming back for more. All right, so we have the North American and Pelican Nebula. They're in Cygnus. I have a wide field and close-up of the Cygnus wall. The wide field is 15 and a half hours. Close-up is 24 hours and 42 minutes. The wall itself is 20 light years long. Okay, this whole area covers 10 times the full moon. Okay, so this is wide field. Hope I don't break it. Wide field. Okay, shot with this little called the Rokinon 135. Okay, and this is one of my first pictures that actually looked decent. I was actually like, all right, maybe I should stick with this hobby. Okay, so we have obviously the North American. You see North America here. To me, it looks more like North America this way. Sometimes you can look at it from a different angle, but I think that looks like the Great Lakes there, Florida, up here in Maine. This out here is the Cygnus wall. Okay, this is what's 20 light years long. So it gives you an idea how big this is. And there's the Pelican. Actually, all this nebulosity is all one cloud, but it's separated by dark planet dust here, so it separates them. That has created those shapes. There's a close-up of the Cygnus wall. Now, this is processed differently. I use different filters, and the filter was designed to target oxygen 3, hydrogen alpha. So we can see the dark lane here that kind of separates the two nebulae. Now, this right here is 20 light years long, and this is where, because there's stars on each side, that they're kind of ganging up on this nebulosity and pushing it all together. Okay. All right, so here we have the elephant trunk, wide field and close-up. Wide field is 12 hours, close-up is 53 hours. Now, the cool thing about the elephant trunk is that they're very, very young stars. 100,000 years old is nothing, that's baby. They're still in their diapers by space terms, okay? So that's wide field. And then we have, this right here is the distinctive trunk part, and it's so densely packed that it stands out even with this wide field. So the wide field again was with the 135. Okay, I should probably just keep it up here somewhere. Hopefully I don't knock it down. And then here's close-up, shot with the Roxy. So different processing up much closer. So the blues tend to be more oxygen, and then the golds hydrogen alpha. All right, and here's the Great Globular Cluster, which we talked about. There it is again, in case you want to see it. The Iris Nebula. Okay, so this is cool. This is a reflection in dust nebula here, and Cepheus, 20 hours. The little iris itself is 3 to 6 light years long. Okay, again, our solar system is 2. Now, I cannot take full credit for this. Mr. Alex over there actually stopped by the night I was shooting this, so he actually pushed the button one night to get things started. It was also a night that Jupiter was in the closest to in its orbit to us. But we looked at it through the behemoth, which looked amazing. I'll think of the word later. I'm sure I will. So, what? That's when it's furthest away. There you go. See, I knew I'd think of it. All right. So here is, thank you for that. Thank you for the assist. So here is the Iris Nebula with a whole bunch of cool dust all around it. So the iris is in the middle part there. With a bigger telescope, you can go anywhere here and shoot that dust, and it's going to look pretty cool. All right. Now I have 3 pictures here. The wide field is what's called the Taurus molecular cloud, which is in Taurus, and it's known to be probably the closest star-forming region to us. The Orion molecular complex is pretty close too, so depending on who you talk to, but it's only 430 light years away, which is very close for astronomical terms. So here we have wide field, all that dust, and I mean, there's all kinds of cool nebulosity and those kinds of things. Like, there's here, maybe I want to try to shoot that later. We've got the long tail there. And the baby eagle nebula down here, which I have a closer up view. And then we for Subaru. You guys seen the car Subaru, right? It has the stars on it. It's because in Japanese culture, Subaru is how they define the seven sisters there. So next time you see a Subaru, take a look at the stars on the emblem. But don't be creepy about it. Okay. So we saw this one already. The Pleiades M45, which can be seen naked eye through the telescope. And then here is the Baby Eagle Nebula, which is one of them. Actually, I just finished processing this one pretty soon, just a couple weeks ago. But anyway, that is just a dark nebula. So there's no energy, nothing going on. It's just dust blocking the stars in the background that creates these cool shapes. But we can also see that there's certain areas that the dust is a little bit more dense. Okay. It can still form stars, still form cool stuff like that. All right, here's the Rubber Chicken Nebula. Again, there we go. See rubber chicken. You can't unsee it, right? Okay. All right. Here's the dark shark. Technically, the official name is just the eye of the shark, and it's a smaller part of a very large molecular cloud. And we have 20 hours, 15 minutes. That wasn't the camera. The camera lens. All right, so here's the dark shark nebula. And now, if you flip it around, though, some people say it looks like a fox or a coyote. So, but I like the shark. I think I shot this right around Shark. Is it Shark Month now? Started off as Shark Week, Shark Month, Shark Year, whatever. But I shot it sometime when sharks were in fact. So here's the dark shark nebula. We do have some cool reflection nebulosity there, the blues there, but it's mostly just the dust. All right, so here we have the Draco Trio located in Draco. Now, these are really small. I shot this with the big scope, and that's all I got there. But it is kind of cool to take a look at. Some I just see the stars in different colors of stars on the background. It's kind of neat. We have the top one is an adjunct galaxy. The middle one is an elliptical galaxy, and then the bottom one is a spiral galaxy at an angle. So we kind of get a little bit of everything there in one shot. Maybe if I get a bigger scope, I might revisit that area. All right, the Whirlpool Galaxy, located in Canis Venatici, which is on the border of Ursa Major, so galaxy type stuff. It was the first galaxy classified as a spiral galaxy, and there's a plume, the northwest plume, which is 140,000 light years long. So what we have here is we have a galaxy eating another galaxy. This is the main galaxy. Okay, here's the companion galaxy that got too close, so now gravitationally it's eating it. Now because of the interaction though, that's all this dust. And who knows, stellar matter, maybe stars, stuff like that. This is the plume that is 140,000 light years big, long. Okay, I know, the numbers, right? Crazy. And it's always neat too to look at these galaxies because you rarely see a galaxy all in itself. Because here we have this tiny galaxy here. We have a little galaxy up there. Sometimes maybe in the game I just scroll around and see little galaxies. Fine. And yeah, you can identify all those and see how far away they are as well. If you really want to nerd out. All right. So here we have the Leo triplet, located in Leo. All three of these galaxies gravitationally interacted with one another, and about 800 million years ago. And we have a tidal tail on the Hamburger galaxy that's 300,000 light years long. So here's these galaxies. So they look. You see right here that we have all this extra stuff here in the galaxy due to gravitational interaction. And then if you see the band here of the Hamburger galaxy, it's a little off even. That's because of gravitational interaction. And then here is the tidal tail, 300,000 light years long. It's a result of gravitational interaction. Just think if you were in a system in the tidal tail, you got flung out of your home galaxy. Well, it might be kind of, maybe you get some pictures of your own galaxy. That'd be kind of cool, but as long as everybody's okay. Here we have the Surfboard and Owl Nebula. It's in Ursa Major. Oops, I forgot to put the integration time. So take a guess. That works for me. Now, the Owl Nebula is a planetary nebula. So this is what's going to happen to our sun when it eventually dies. It's too small to be a supernova to be a black hole. So what's going to happen is eventually when it uses up its fuel and it starts creating heavier elements like iron, it's going to puff out. Okay? So that's what planetary nebulae are really cool. They're usually pretty small. But here we have the Surfboard Galaxy up there in the corner and then the Owl Nebula there. So it is at a fraction of the mass of our sun now because it's shed out all of its gas, or most of it. Okay? And there's a white dwarf in the middle. Very, very dense. Like a teaspoon of white dwarf matter is something like the Eiffel Tower, mass-wise, or something like that. All right, so here we have, all right, so we talked about this, looked at this already, the crowbar and whale. And you can see with the whale galaxy, that's a little irregular because of gravitational interaction, but it also has a little companion galaxy there too. So it's floating around in the sea of space with the whale galaxy. All right, fireworks galaxy, 24 hours, 20 minutes. Tons and tons of star formation. It's a very active galaxy. It averages about 10 supernovae in the last 100 years, and Milky Way, we average about 1 every 100 years. So very, very active. I always think it kind of looks like an eye there in the middle, doesn't it? We also have an open star cluster there, and you'll notice that there's a bunch of gas, dust. I mean, there's a bunch of dust in the frame as well, because it's a little bit more towards the north celestial pole, which has a lot more of the dust. So we also have some little galaxies if you wanted to find those there. And it also kind of looks like it's swirling around in the dust, doesn't it? All right, let's see. Now this is my most recent project I completed. The hair clip or needle galaxy in Coma Berenices, which is just the hair constellation. 31 hours, it's edge on, and it's brighter than Andromeda. So, and it is a pretty tight crop too, but a straight edge on, and you see why it's called the needle galaxy now, right? And we have the little galaxy up there in frame as well. So. All right, the pinwheel. Okay, so this is really cool. This is just dumb luck. Okay, I did not plan this. I shot this around May 19th, 2023, and as I was finishing it up, I was like, all right, I got enough time. A star decided to go supernova. A star blew up in another galaxy, and I just happened to be shooting it. So I was like, all right, I'm going to go back for one more night. So I shot it for one more night to do a side-by-side comparison. So this galaxy has 1 trillion, that's with the T, 1 trillion stars. Now keep in mind too that it is 21 million light years away. So what does that mean? It means the star exploded 21 million years ago. That the light traveling through the vacuum of space at the speed of light has just now reached us. Okay? Yeah. All right, so there's just the picture I planned on having. You see the little companion galaxy up there, but you see why it's called a pinwheel. Due to gravitational interaction, that's why we have a little bit of the irregular shape as well. And here is the supernova. So we can see, now the one on the right is just one night's worth of that, so you don't have as much detail, it's not as bright. But you see just the difference of a couple days to start, and that's 21 million light years away. We saw that. Came to us, yeah. There you go. All right, so here is the galaxy I showed you earlier. We have a total of 26 hours. So this dusty stuff is called integrated flux nebula, which is a somewhat recent discovery, and it's only prevalent around the celestial poles, the north and south celestial poles. So what this is, it's gas and dust just hanging out just outside of our own galaxy. And it's illuminated by the energy of our galaxy. So instead of like a star or a group of stars that illuminates the nebulosity, this is illuminated because of the energy from our own galaxy. So this stuff is very faint. So you need a lot of integration time. But these galaxies are kind of surrounded in it. And then we have the cigar galaxy in the lower right corner that's massive star-forming region that's so much that it's shooting out all the extra gas and dust that's giving it the reds on each side. All right, and here's our Triangulum galaxy. It's in the local group. So there's us, Triangulum, and Andromeda. And Triangulum is the smallest, so it's about half the size of Milky Way, but it's very close, so it's still Looks pretty big. All those red pockets are nebula in another galaxy. So if you have a big enough telescope, you can actually take pictures of nebulae, star-forming regions in another galaxy. They're so big that they have their own NGC categories. And then we have Andromeda. I've got 2 pictures here. I've got 10 hours wide field, and my longest project to date, 69 hours. It's a 4-panel mosaic. It's so big, using the velocity, I couldn't fit it all in one frame. I couldn't fit it in a 2-panel mosaic, so I went with 4 panels. And I shot it for a very long time. So it's 25 to 50% more massive than our own galaxy, and it's 2.5 million light years away. So again, the light that's hitting us now is what the galaxy looked like 2.5 million years ago. Okay? And we will collide with Andromeda in 4 to 5 billion years, so I don't think we have anything to worry about. But then we'll become one with it, so Melkomeda, I think is what they're playing with. But in 1925, it was confirmed as a galaxy. For the early on, it was believed that we were the center of the universe and all that kind of stuff, where scientists were lynched in the streets for saying that we weren't the center of the universe. But it's wild to me that in 1925 it was actually confirmed as a galaxy. I mean, that seems pretty soon as far as space stuff is concerned. So here is the wide field with this. And here's the close-up. That's the 4-panel mosaic. Andromeda also has 2 satellite galaxies that are orbiting around it that's stuck in its gravitational pull, and those both are elliptical galaxies. And you can see all the red there, that is nebulosity, star-forming regions of another galaxy. And some of those regions are so big that they have their own NGC categorizations. And you even see, even beyond that, I mean, I probably could have made it even bigger because you see how far the arms are spiraling out there. Okay. And here we have some of my sun stuff. So these telescopes here. So you'll see how different the sun is from picture to picture. So same sun. I didn't go anyplace else. Same backyard. But see how different that looks. Those dark spots are sunspots that create solar flares. And the stuff on the side, those are prominences. Okay? So a prominence is not a sunspot. So a prominence is not like a flare. A prominence is just a magnetic loop of plasma around the sun. So the sun flares come from sunspots. Okay? So those are the dark regions there. Same sun, same backyard, just you can see that wasn't very active that day. We're going through what's called solar maximum, which is the sun is very, very active when the poles actually switch. Okay, it's an 11-year cycle. So we're getting close to solar maximum, which is the when the sun is the most active, which is why we have all the auroras lately and the disruption in electronics and those kinds of things. Okay. Then there's the 11-year cycle when it's solar minimum, where there's not a whole lot of cool stuff going on. Okay. Another full sun there, and here's another one. Those prongs are just enormous. The Earth compared would be a tiny dot. You could barely see the Earth if I had the Earth right next to it. It would just be a teeny tiny.
You were using a Joppa filter?
I was, yep. Now that's a special, that's good. It's a specially designed hydrogen alpha filter, specifically for the sun. So, what you do, this is the filter for the sun, okay? So these telescopes right here are not designed to take pictures of the sun. You do not want to look at the sun, nothing. But what you can do with a filter like this is you hook it on back here, and boom, you've got a solar telescope. Hook it right here, solar telescope. Okay. It doesn't work with reflectors because they're reflecting sunlight off of mirrors, which you don't want. That's a bad idea to begin with. Okay. So you can add this to any, usually a refractor, any refractor. And it's a hydrogen alpha, so that's the, this is called a chromosphere model. So that specifically takes pictures for lots of everything but the specific wavelength of the chromosphere. So this filter right here is an E telescope into a solar telescope. All right, and then some close-ups. Now this is when I was still kind of, I was getting my focus down a little bit, so it does look a little blurry. A person who's better at this, it would look much better. But I was spoiled because with my deep sky rig, it focuses for me automatically. So I had to learn how to focus again. Here's some more proms or prominences. Oops. Okay, there we go. A sunspot and prom there. Now this is even closer up. So those pictures were taken with the smaller scope. The larger scope here, you'll see it looks a little more feathery, right? Even though it is a little bit out of focus, but the sun is a big ball of gas. Okay, it's not on fire or anything like that. It's a big ball of moving, circling gas. So it's going to look like this up close. Okay? And those are some huge proms. I mean, the Earth, you could probably fit, like the lengthwise, I mean, thousands and thousands of Earths in that prom right there. And here's another close-up. This is somewhat recent too. The sun is very active, shooting off all these kind of cool free-floating prominences. And we have one over here. Now this is kind of a cool phenomenon called a philoprom. So a filament right here is exactly like a prominence, but it just depends on where it's at in relation to the on the sun's surface to Earth. So if we're looking at it edge on, it's a filament. It's exactly the same thing as a prominence, but if it's on the limb, it's a prominence. Okay? But this thing is so big, it snakes around there, and even shoots off the edge of the solar disk there. That's a philoprom. And here's just a wider view of that there. X marks the spot. That was really a really cool thing to see there. And here's a wider view of that. And there's that part. There's kind of a cool loop or arch. Yeah. And all this stuff is luck. I mean, you can look up, there's websites and apps and stuff like that, which I can go into. I know I've kept you here a very long time. That you can see the activity of the sun almost real time. So I knew kind of the sunspots, and you can track those, but as far as the prominences, that's usually dumb luck. So here's one there as well. It's always cool to get you can get a prom, a sunspot, and a filament there. Here's a close-up. I have rotated the camera to get a different angle, but there we go. The surface of our star. All right, we reached it. You guys survived. All right. So,
I think that's hysterical, right? That's him talking about astrophotography to other people.
all you guys. So,
Anyway,
are you overwhelmed yet?
wasn't this great? And I'm so thankful that there's no quiz. I'm just saying.
No. All right.
Always give an honorarium to our lecturers. I feel like you're way more than this. Thank you. And thank you for all of you for being here, for staying, for listening. If you have other questions,
I'll stay as long as you
Matt
want.
will hang out. He's got to pick up his stuff anyway. Shannon, thank you for keeping the library open for us tonight. Please remember, if you like this lecture, join us. There are forums out there. Thank you so much.
And
Matt,
real quick,
you.
yes, you're welcome. And you guys, I want to leave this with, as Voyager 1 was leaving our solar system, it turned around to the picture. The blue dot, that's us. That is Earth as Voyager 1 in